If you want to create a swirly particle simulation or create complex volume trails, just using a curl noise might not be enough. A better technique is to create your own vector field that combines nice and swirly motion, but also offers a lot of control. This tutorial shows you how you can use guide geometry and generate circular vector fields around its points. We will learn about the cross product, calculate those vectors, and finally advect particles with it. As usual, we create an empty geometry container, dive inside, and inside the geometry we will create a sphere, set the primitive type to polygons, and set the frequency to, let's say, 3 for now. So we have a very low resolution sphere over here. And we want to make a little irregular shape, so we create a mountain top to deform it a little bit. Put the flag on here, and let's set the height to 3.5, and we'll keep the rest as it is at the moment. Zoom out a little bit, perfect. And next thing we want to create is some normals. So let's hit tab and type normal. Connect that and set the normals to be point normals. And if we click this button here, we can check them. So you get nice normals over here. We want to use this geometry to create a very irregular but very swirly velocity field around that. So in order to make a field or volume, we need to create a volume first. And we want the volume to have roughly the size of this geometry. And in fact, it should be a little bit bigger so that we have some voxels around this geometry to work with. So we continue with the bound sub. This will create a bounding box around our object. And let me deactivate the normals. And since we want to have some space around our object, we will type in some padding values here. And I think we can type in 2 in each axis. So lower padding and upper padding. Then you see you get the double the size of the actual bounding box around here. And we will use that as the bounds for our VDB. So the next thing we need to create is the VDB. So we type VDB. The name of our VDB should be vel for velocity. It's a fork volume and the type is vector float. And vector type we can set to displacement, velocity, acceleration. And the voxel size maybe 0.2 for now. We can change that later. So by doing that, you get an empty VDB. And since VDBs are sparse volumes, you can see that there's nothing in here. So you need to activate a certain region in your scene to be visible for the VDB. And for that, you can use a VDB activate. We connect our VDB and we connect the bounding box that we want to use as bounds for our VDB. And we connect that to the second input, which says region to activate. Okay, so let's check that out. Nothing has happened here because we need to set our VDB activate to look for the reference. So just click that and then you actually get a nice VDB in the shape of our bounding box. So we now have those voxels to work with. Okay, now we need to calculate the actual velocity volume that we get our nice swirls around the geometry that we just created up here. To do that, we use a volume VOP. And we connect our volume to the first input. And let me scroll up a little bit, push that to the side. And we connect our geometry with the point normals here to the second input. And before we dive inside here, let's jump into some theory first and let's talk about the cross product. The mathematical operation that we will use in our scene here is the cross product, which is super useful. And I built this little visualizer here to show you what it does. So imagine we have 2 vectors, which is the red vector here, let's call it vector A, and the second one is vector B, and they point in different directions. And if you create a cross product out of those 2 vectors, it will create a plane between those 2 vectors, and the result of the cross product will be the normal of this plane here. So you can see this is our result here, and it's exactly the normal for this plane. So if I select one of my vectors and move it around like that, you can see that the result will change and it will always point in the direction of the normal of this area here. And we can use that in our case. So let's take one vector and make it more or less vertical here, so I can illustrate what we will do. Let's say this is the normal of our geometry, and this is the position of a voxel somewhere in space. So we can calculate the difference between our voxel in space and this point here, where the normal sits on. So we have this vector here. And the second thing we want to do is build a cross product out of those two to create this one here. And then we will use this cross product, so this direction, and write it into this voxel here. So the result of our calculation in this case, so the normal crossed with the difference vector between the voxel and the found point, so this one here, will result in this vector. So if we write this value now in this voxel, you get an arrow that points over here. Now let's imagine we go in the next voxel, go over here. Then you can see that the vector changed and now the direction points to here. And if I zoom out a little bit, let's go over here. Now the vector points here. And if you do that all the time and go around it, you will see that you will get a circular vector field swirling around this normal here, the green vector over here. So you do that on each and every voxel surrounding our point with the normal. And you will result in nice swirls around this geometry. In that case, you can see that the length of our resulting vector also changes with the length of one of our components here. But of course, you can simply normalize this vector and then it will always have a constant length of 1. And this is basically what we will do now. So back in our scene, we know what to do now. So let's put the flag on the volume VOP and jump inside, and let's make some space here. We can delete the output here because we don't want to write anything into density. And first of all, I want to bring in the geometry that we created with the normals, and we do that as a point cloud. So let's create a point cloud open. And let's connect the second input to file, because the second input is where we connected it to the volume VOP. And we now want each voxel of our volume to sample this point cloud here. So each voxel will look up in its own position if there's a point of the point cloud nearby and can read out those values. So let's connect the position of the voxels to this position of the point cloud. And let's just leave all the settings as they are in here. So maybe we can increase the search radius to be 1 so that we don't end up with voxels that can't find anything. And on the other side, we now need to specify what kind of attributes we want to read out from the points that have been found inside this point cloud. So again, we use a PC filter. And the first PC filter should look for the position of the point. This is correct. And we copy that one here, connect both. And the second should look up for the normal of the point. So let's change the P to normal. And I like to write in here what they do. So this is filter position, and this is filter normal. And now let's first of all think about what we want to do here. So each voxel now finds the closest point in the point cloud. And the first thing we need is the vector that points from the voxel to this point from the point cloud that the voxel could find. So we will subtract. And the vector should point to the point in the point cloud. So this should be the first element in our calculation. So let's put in P. And the second input should be the position of our voxel. Then we can normalize this vector here so that we get a constant value, constant length of 1. So normalize that. So now we have the vector that points from the voxel to the point of the geometry. And now we want to cross this vector with the normal vector of this point to get like rotational fields around this point. So let's do that. We use a cross product and we connect our normalized vector and the normal of the geometry. Move it over to the side. And then we need to store this value that we get out of here in the volume. So we use a bind export to write out those attributes. And the name should be vel, so we can write into the velocity grid. And the type is a vector. And we just connect this one here. And you can instantly see that something happens here. So let's go back one level. We have our setup here. It's a volume fork representation, so you don't really see any directions, but you can already see that something changed here. And if you go to the mountain, for example, and change the height, you can also see that the result also changes. So let's put it back to 3.5. And let's visualize our field that we now generated. A super easy way to do that is using volume trails. So we can use points from volume, for example. And we can simply connect our geometry to that. So let's check it out. So this is now a lot of points. So let's decrease this to 0.3 point separation maybe. And up the jitter scale so that the points are really like jittered inside of the geometry. And let's switch to different wire styles here. So if you hit Shift S, you can actually change how those wires should look like. And now we have our points here. And now let's use some volume trails. On the left side, you connect the points that you want to trail. And on the right side, you have to connect your velocity volume. And in our case, if we connect that, everything should work right out of the box. And this looks really cool already. So maybe we select the volume trail, make the trail length longer. So maybe 5. And maybe we want some more points here to have more trails. So let's decrease the point separation to 0.2 maybe. And then you get a good idea of how this looks like. So you can already see this is a very, very interesting vector field. There's a lot of swirly motion and a lot of direction changes. And you can imagine that now all those swirls here always rotate around the points of our guide geometry. And where they're close together, they influence each other. So if we go back up here to the mountain and, for example, offset the mountain by 1 unit, you will see that you get totally different results. But again, in the same look, and you get super interesting swirls around here. You can see that at the moment, the resolution of those curves here is pretty low, so they look very choppy. Of course, you can select the VDB and make the resolution finer here. Or you can also resample the volume trails after they have been created. What I also like to do is select the volume trail, deactivate visualize velocity, and then simply append a color sub, connect that, set it to primitive and random. I think it's easier to see the shape of the whole structure. So I totally love those volume trails. I did a tutorial about that one in the past as well. So if you do more of them, this is really great. So the structure itself looks very interesting already, but of course it's cool to have velocity, volume, and advect some particles with that to have some interesting motion. And maybe we can use the volume trails to spawn some particles. We could try that. Let's maybe decrease the number of our points here a little bit. Let's go back to 0.2, that we don't have too much. And we simply create a POPnet. And as a emission geometry, we can simply use the volume trail here. So we don't need the color. Just put that here in the first input. And let's take our volume that we calculate up here and put it in the second input. Put the flag on it. And if you hit play now, you should already see that some particles are generated. Let's activate the real-time toggle over there. And let's just dive inside and change some things here. So we can get rid of the merge. Click on the source first input. And first of all, let's deactivate the guide geometry so we don't have all those blue lines here, and maybe get rid of the world grid. And we want to advect our particles by the volume. So let's create an advect by volumes, pop advect by volumes, put it in between. And since we connected the volume to the second port of our POPnet, we can specify that here. Velocity source is the second context geometry. Field name is vel. This is already correct. And we want to set the advection type to update velocity so that the particles really follow exactly the velocity. If you set it to force, the forces will add up over time and they will fly away. So we just set it to update velocity, keep it like that. And if we now hit play, we should already see something very nice. So you can see that the particles already follow our field very nicely. So one problem is they all have the same color and it's pretty hard to understand what's going on here. And some of them get stuck. So on the left side here, you can see that some of them, if they reach the end of our field and there's no velocity anymore, they will stop. So it's maybe a good idea to get rid of particles that have no speed. So let's do that. We use a pop kill for that. And you can see that in the pop kill, you can define some conditions when the particles should be deleted. So if you just activate that and hit play, you can see that all of them are now killed because the attribute or the variable dead is set to 1. But we only want to do that if the speed of the particle is 0. So let's get rid of that. And we type if, open parentheses, and then we need to check if the length of the velocity vector is 0. So if the length of the vector v equals 0, oh, we have to close the parentheses here. So if the length of the vector v equals 0, then we want to set dead equal 1. So if the length of the velocity vector is 0, which means the particle is not moving anymore, we want to kill it. Then it gets deleted. So let's hit rewind and check again. And we should be able to see slow particles, but there shouldn't be any particles that stand still. And now maybe let's change the color of the particles here. So let's say we want to have particles change their color depending on their speed, for example. So we use a pop color. You can also do all of this stuff outside of the VOPnet, but the pop color has some built-in functionality which makes it easier for us. So you can click on the pop color, set the color type to be a ramp. And by default, it says the ramp is remapped on the normalized age, but we want to change that. And luckily, there's a preset for speed. So just select that. And now you can see we have darker particles and brighter ones. So let's change the colors maybe. We can, for example, use a purple and then we use like a greenish blue. Play again. And then you can see the slower ones are purple and the faster ones are this greenish blue over here. That looks really nice. Maybe we can make the particle size a bit smaller so that it looks more like dust. And then we need much more particles. So let's click on source first input, birth tab, and we increase 5,000 to 50,000 particles per second. And then you get this really, really nice dense particle flow over here. Of course, this is now very interesting, but also pretty static. So one thing you can do is just animate the geometry that generates this nice flowy vector field. The only thing you have to keep in mind is that changing the geometry also forces the VDB to update, and this can take some time, but actually what you can do is click on the VDB and reduce the resolution again a little bit, because for the advection you actually don't need such a high resolution. So let's set it back to 0.2 so that it gets calculated pretty fast. And in our mountain, let's go here in time. So because let's put the flag on it and check it out. So if you type something in here, an expression, the noise inside of your mountain will change over time. In this case, I think we can write $t, so the old H script style expression, $t divided by 20 maybe. So this means seconds here. And if we hit play, we can see that it moves and it's a little bit rough. So we can go into roughness down here so that we get a super smooth noise, so we don't get the little jitters in there. Hit play and then it's nicely changing over time. Maybe we need some more time here. 600 frames in there. Yes, that's very cool. And if we now check the volume trails, for example, or maybe the colored volume trails, we can see that they change over time. Of course, this is not very stable. The colors change in each frame and the trails get built and deleted like crazy, but that doesn't matter in the POPnet. Put the flag on the POPnet, hit play again, and then you can see that you get a very, very interesting particle field. I hope the particles are not too small now, so maybe I'll make them slightly bigger, maybe 2 pixels. This is a lot of particles now. But you can see that you get super interesting structures and they always swirl around the normals of the points of your geometry. What I also like is that you can now add geometry to this setup here. So let me show you an example. Maybe we reduce the number of particles in that case a little bit. So 10,000 per second should be fine. And if we go back one level, after we created normals for our geometry, let's put something in between. So we create a merge, put the merge here, just that we have one after this one, so that we can plug in additional geometry after that. And I will create a curve. And let's click on the curve, hit enter in the viewport, and then maybe click here, 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 here. So just that we have some points. Let's put the flag on it. And let's use a resample. And I just want to have a smooth curve. So let's take that. Set the treat polygons as subdivision curves. So we get nice smooth curve here. And we want to create some normals which point in the direction of the tangent. So we can activate tangent attribute, and the name for this one should be n, so that it's normals. And if we check that, you can see over here maybe, you can see that the normals now point in the direction of the tangent. And we do that because our whole setup is built to react to the normals. So let's make it easy for the setup and just name the tangent normal. And if you now put that in here, whoops, it will also write its data in our velocity volume. So if we check the volume trail, maybe with colors to make it easier to read, you can see that some things happened. And if I put the template flag on our curve, you can see that wherever our curve penetrates the other geometry, you will get some swirls around that. So you might be able to see that if I click on the curve and change it here, you can see that the resulting velocities update in real time here. So you now have a big swirl up here, for example, in this area, or here on this side. You can create very, very interesting shapes, or maybe something like that. So you get nice big swirls here coming out of the whole structure. Yeah, the point is just that you can add some guide geometry in here to change the shape of your velocity volume totally, and you can still use that and advect your particles. So let's hit rewind, play again, and then you get this nice big swirly motion up here. What's also super interesting, if you want to have a totally different look, is if you don't use the volume trails as a source for your particles. So you spawn particles somewhere else. So for example, if you take, let's take a circle and make that kind of small, so maybe 0.2, so that it sits here in the middle. Hit rewind and just connect this to the first input of your POPnet. You will see that now all the particles are spawned on this side, on the geometry. And if you now hit play, you can see how the particles actually make their way through your velocity volume. And this is a very interesting motion, and it's definitely something totally different to a curl noise or something like that. So the shape itself is so much more interesting and follows some guides and some structures which you can't achieve with a normal noise. This technique can be a starting point for a lot of very complex effects, but it's also great to just steer the velocity volume exactly in the direction that you want, and that you have as much control about your particle simulation as possible. I hope you liked this tutorial as usual. Let me know what you think, and I'll see you in the next one. Bye bye.